Next example. Let's look at an elevator that's accelerating upward. We take our box, once again, we put our box in the elevator, and this elevator, there's the cable up there, it's pulling that elevator up, it's accelerating it upward, and we'll now look at what the normal force is on this box riding in the elevator. So there's our sketch. Let's draw our free body diagram. Identify the object of interest. It's still the box. It's not the elevator. It's not the elevator cable. Choose a coordinate system. Up as y and horizontal as x. Still a good coordinate system. Place that object of interest at the origin. Identify forces. So again, we only want the forces on the object of interest. So sometimes people get confused. They think, well, there's a force pulling on the elevator. That's true, but the elevator is not our object of interest. All we care about is what the box is experiencing. As far as the box is concerned, it only sees gravity and the normal force between the elevator and the box. So one way of kind of thinking about this is the elevator is getting pulled by some force with that cable, and it's transmitting the knowledge of that force to the box via the normal force. But as far as the box is concerned, it doesn't know about the cable pulling the elevator at all. It only feels that elevator floor underneath it, pushing it. So that's it. We just have two forces for our object of interest. And if we do Newton's second law in the y direction, we've got N minus W. Whoops, I used really bad letters here. I had E for Earth and E for elevator. Let's say that this is an elevator car, so I'll write C for the car of the elevator. W, Earth on box. Okay, C for elevator car, E for Earth. This is a problem we encounter a lot in physics, is that there just aren't enough letters in English to label everything you want to label. Unfortunately, sometimes we end up using the same letter to represent completely different things. You might have noticed that already, because I'm using N for normal force, and we've already said that capital N also represents the unit newtons. So that can be a little confusing when you write normal force equals 100 newtons, like N equals 100 N. And you have to understand from context that the N means two completely different things within the same equation. We only have so many letters to use. All right, back to this problem. Newton's second law on y, we add the forces in the y direction. There's the positive normal force going up. There's the negative gravity force pointing down. That equals ma(y). This acceleration is not zero because the box is riding along with the elevator, which has some acceleration. So the right-hand side is not zero, and we find that the normal force of the elevator car on the box is ma(y) plus the gravity force, mg. If this elevator were not accelerating, like once it stops, then this term goes away, and you just get that normal force that equals the object's weight. But when the elevator is accelerating, the normal force has to be stronger in order to accelerate that object. So this is a stronger normal force than it would be if the object were stationary. That's why when you walk into an elevator and you start it moving, during that period where the elevator is speeding up, you feel extra pressure on your feet. You might feel like you're getting heavier. That normal force between your feet and the elevator car has gotten big while the elevator is accelerating. Conversely, if you send the elevator going down, that would give this a minus sign, and the normal force you would feel would be less than your weight. So when the elevator accelerates downward, you feel lighter than normal. If it accelerated downward really fast, you might feel weightless. That would be poor elevator design because people would freak out and get sick.